Welcome back to chapter 8 of A2. Previously, we already looked at some fossil stuff, right? Newton's law of gravitation. You remember it? Don't tell me you forget already. Too fast, too fast. But today, we're going to continue the story a little bit more about gravitational fields. Remember, I briefly mentioned this thing? I say, oh yeah, it's like electric field. Remember? Fields, the line, the arrow. But today is all about the fields. Gravitational field strength. Okay? Previously, we already looked at the force. Okay lah, this part done already. Ayo, what kind of line is this? Force done. Today we're going to focus more on these arrows, the fields, and what do they mean. So by the end of the video, you should be able to, firstly, derive an equation for the gravitational field strength. Oh, there's an equation, you know. Okay, do you know what it is? Maybe, maybe not. Okay, never mind. We're going to learn how to derive that. And then, of course, solve problems with the equation. There'll be some examples here, but not too many, so we'll try to keep the video short. And then lastly, we want to know, what does this sentence mean? Appreciate that G is constant on the Earth's surface. I promise you, it's nothing new. You'll be shocked when you see it, like, oh, it makes sense now. Okay, anyway. So these three things, make sure you know these by the end of the video. Now, without further ado, let's take a look at gravitational fields. Now, you can ignore the stuff on the right side, but here's a little simulation. This sphere, imagine it's the Earth or something, I don't know lah, okay? This sphere, because it has a mass, it has a gravitational field, and the field looks something like this. Wow, look at that, 3D. Notice how all the arrows are pointing to the middle. Okay? But then you see the arrows far away, right? Very small. Means the field is very weak. But as you get closer and closer to the middle, the arrows get bigger and bigger. See, if I take away the sphere, right, you can see in the middle here. What is this? You see the arrow so big? Okay, you can zoom in. Wow, can zoom in some more. See lah. The arrow very big in the middle, okay? That's because our good old sphere is there. So that means if you have some particles around you, they will like suddenly, they'll very quickly stick. Because when they are very close to the sphere, wow, the field is very strong. So just like last time, electric field very strong, the particle move very fast. So here, near to the surface of this sphere, all these particles are attracted, gravitational force, attracted very strongly, and then they'll very slow, suddenly zoop, stick inside. So this is how a field looks like in 3D, in real world. I know in paper we only draw 2D, but this is how it looks in 3D. So to make our lives easier a bit, here's a 2D version of it. Okay, there's actually many more arrows, but here only got one arrow. This is just one of the arrows. Okay, G here is the gravitational field vector. Like, if I drew all the arrows, they'll be all pointing, but I only want to see one. Okay, so this M here is our big fat object, you call like a planet. And this M here, this small m, is what we call a test mass. Testing mass, like, what if there was something there that has a mass m? That's a test mass. Okay, so at this position, there will be a field vector, the field arrow, the gravitational field arrow that is roughly this long. If you go closer, the arrow is much bigger because the field is much stronger. Okay, so go around here, much stronger. If you're very far away, like we saw just now, the arrow is very small, up in the corner. How to see? Okay, so we're going to use this idea of a test mass to derive the equation for gravitational field strength. Here's our little Earth, planet, whatever you want to call it, a mass or things like that. So here's one, kind of like this planet picture here, but I'm just going to draw it like that. Okay, so this first object has some mass m1. Let's call it m1. How about that? So m1. And then I'm going to put my test mass. I keep thinking electric fields. And at this place, it's going to experience some electric field that is quite small. Okay, I don't want to draw the electric field, so just so you know, like we saw just now, there's already electric field. But because there's a electric field, oh my goodness, gravitational field. So because gravitational field, there's gravitational force, Fg. All good? You say, Miss, isn't there two force, one acting on this small mass, one acting on the big? Yes, there's two because of the Newton third law pair, but we only want to see what's the force acting on this test mass. So this test mass has, I don't know, m2, and this is the test mass. Okay, so if there was a mass there with some m2, whatever it is. Okay, so I think we got set up. All right. So there will be, we want to ask the question, what is the strength of the G field here at the test mass? Question mark. What is the strength of the G field? I know just now we already saw an arrow, but we want to find an equation that can calculate that. And you need to know how to derive this equation, because in exams they will ask you, this equation, how you define? Okay, sure. So what we're going to do is we're going to use our Newton's law of gravitation to help us out here. So let's say we use the gravitational force per unit mass and use that to define our gravitational field strength. If you're wondering, Miss, where this come from? Suddenly come out one. Nah, last time you already do F equals to QE. Right? Then F over Q is your electric field strength. F is a force, Q is a property of your charge. So we're doing the same thing here. Okay, force per unit mass. So we're doing force per unit mass. Force, mass. And that will give us our gravitational field strength. So G equals to the force acting on that point mass, okay, this Fg here, divided by the mass of that thing, okay, m2. All good. Okay, then we are stuck. Okay, how to proceed? Is this the equation? Done already? Okay, yeah, you stop there. But we want something more elegant. So this Fg, we know from previous example that it is related to Newton's law of gravitation. So this one, we know the equation from the previous video. So let us sub it in. Why not? There's just one problem. This one equals to G m1 m2 over r squared. We know m1 m2 we already defined. What is r squared? R here we're going to define as the distance between the center of this sphere. So let's say I draw a line down lah, and I need some space right off this. And this test mass right here. Let's call this whole distance h lah. Or r, never mind, let's call it r here. R. Separation distance between two masses. Okay, so we're ready to go. Okay, let's plug in our stuff. So, yes, just now we know Fg is, thanks to Newton's law of gravitation, we know the force between these two objects, the big planet and the small mass, is gmm over r squared. So I put a comment speech bubble. Now, what is it? So this will be G m1 m2, the m2 is still down there, r squared. R squared is the distance between these two objects. And hey, look, we can simplify a little bit. So here we can m2. That leaves us with gm over r squared. So that is how you can calculate the gravitational force per unit mass, or aka the gravitational field strength. Let's put a comment here. Gravitational field strength. Of what? Of m1, the big one. Okay, we don't care about the small one lah. Okay, so gravitational field strength of m1 at some distance from the center, at r distance, because we define r as a separation distance from the center of the big one. This is an important one you will want to remember. Ding, 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 ding. Okay, and you also need to learn how to derive it. They say, how you get this equation? Prove it. Then you have to think of, okay lah, at first this, then Newton's law, plug in, and then get this. Okay, you must know how to do this. Also, what is the unit of this thing? Interesting thoughts. Let's think about it a little bit. Before that, we use force divided by mass. So this one should be Newton divided by kg. Lor. So that's our unit. But Newton divided by kg has another equivalent. Okay, let me write on the side. Newton is kg ms -2. Mass, acceleration. mass times acceleration. Then divide by kg. Then the kg cancel out. So actually, you can have another unit, which is meters per second square. Where have we seen meters per second square before? Oh my word. You say, Miss, isn't that acceleration? We're getting there. It's related to acceleration. Well, it is acceleration because meter per second square. Okay, so that's the first part. How do you find the gravitational field strength at any point in this field of this big fat one? So the orange color one is the field. So you put your test mass anywhere, you can find the gravitational field strength with this equation. Now we come to an interesting case. Now what if it's a planet, like our planet Earth? My planet Earth, where is it? This one, very small planet Earth. Is what happens when you reach the surface of the planet. Cases will be a little bit different. Okay, when you come to the planet's surface, let me attempt to draw a circle. There, something like that. Okay, and this is center. But when you are, like, say, very close here, we want to say, what is the gravitational field strength there? Okay, so we try. We use the formula we just derived just now. Gm1 over r squared. M here will be the mass of the Earth, so I'm just going to write ME for now, because now we're at planet. Let's use Earth. Okay, ME is mass of the Earth. Go Google and see what's the mass of the Earth. And r squared is the distance. Actually, it disappeared. Great. Fantastic. Here, let's say you're on a mountain top. Okay, there we go. So let's plug in all the values we know. We already did ME. But what is the r squared? R is the distance between the center and this point. So for planets, you want to separate it into two sections. The first section is the radius of the planet. I'm going to use big R as the radius of the planet. What's the radius of the Earth? I'll go and find out later. You can Google and see. But then there's this tiny little thing we call height. You know why we call it height? Because, if you are jumping above the Earth's surface, you have some height. And of course, you have the Earth's radius, which comes up to the floor only. Okay, so that's what the height is. We're trying to find what is the gravitational field strength of, if you're roughly near the surface of the Earth like this person. Okay, so we do this Gm over, now the R is R plus H squared. That is the gravitational field strength for any object near the surface of the Earth. Okay, this is only for near the surface. And then we are going to do some simplification. Since near the Earth's surface, H is very, very, very small compared to R. Okay, we are going to do some shortcuts. We are going to say, since H is so small compared to R, you can ignore the H. So you do H equals to, G equals to Gm over R squared. The small H disappear already. It's just Gm over R. Because if you calculate and see, you take the mass of the Earth plus some height, you'll find that it's not much of a difference. Okay, so this is the case. All right, and actually I have a simulation for you to see. Yes, this one they calculate for us already. So Gm over R squared, right? Here we can choose Earth. We got Earth. G is a constant here, 6.67. M is the mass of the Earth. Well, they already chose for us 5.9. Wow, very heavy, or times 1024. That's the mass of the Earth. And the radius of the Earth is 6.37. So, calculate 9.81 meters per second square is the gravitational field strength at the, or near the Earth's surface. So, anywhere along here is 9.81. Does that ring any bells? Have you heard 9.81 before? Okay. 9.81. So familiar. 9.81 is what in AS we call the constant, because we only stick in the near the Earth's surface. So anything you MG or 9.81. That is only for if you are near the Earth's surface. If you're a little further, it'll be a little bit different. So yes, that's where we get our 9.81 from. This is our 9.81. Let's use Newton kg. Okay, there we go. Near the Earth's surface. But actually, for any large r, your G field will be constant because... Why is it constant? I thought you just like say, Miss, so you say your field come out like that is stronger near the object, but further away is weaker. Yeah lah, but because if you zoom into near the surface of the Earth, the lines of the field are almost parallel near the surface lah. What do I mean by that? If you zoom in, okay lah, if you zoom out a lot, you see the lines are not parallel. Okay, they're close and then they're very far. But if you zoom into the curve a bit, you see, they are kind of not as radial. This is what we call radial. If you zoom in somewhere, maybe into this section, then it become like straight. You see, you look outside your window, right? The floor is flat. Almost flat. The Earth is curved, but your floor looks flat because you zoom in a lot. And then when you zoom in a lot, you will see it's like, almost parallel. So when it's parallel, this is what we call a uniform field. Okay, uniform. So near the Earth's surface, it's almost uniform, and you know it's 9.81 Newton per kg. That is our gravitational field. If you are wondering, the last thing we need to know here is, so we know, okay, at first, you are very far away, you come closer, okay lor, you can calculate it with gm over r. It's a very important equation. And then, for a special case for Earth, if you come right close to the surface, we can pretty much ignore that small h there, and it's roughly 9.81, a constant. So you must be able to explain why is it a constant and make sense of it, why it's a constant. Okay, that's one more little thing for you to see. Now, if we take the values of g, they use a here, like ag, okay lah. Anyway, so at the surface is 9.81. As you go up a bit, it maybe drop a bit, become 9.59. Then drop some more, 9.42, 8.76, 5, 4, 3, 2, 1. Does it ever go to 0? Good question. I want you to think about it. Will the gravitational field strength ever go to 0 when you're super far away? Okay. How would a graph look like if you took these values, you take this one, the r, then you take this g, plot, 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 plot. How would a graph of g against r look like? That's the final thing you need to know for this video. Here's how the graph would look like. If you are lost, you can go ahead and try plot out every single value from the simulation, but the highlight is this, g against r squared. So that's the relationship. G is proportional to 1 over r squared. And 1 over r squared means your curve is going to look something like this. Yeah, proportional, kind of. Okay, so it's going to keep going. So if, for example, if your radius, okay, let's start off with here, this point. This is at the surface of the Earth. So that's r. And we already found the value just now, that's 9.81. Okay, so as we go further and further, let's say maybe we go to 2r. 2 times the radius of the Earth. What will the g value be? You can play with ratios here. So 1 over 2r squared. So what will be the ratio, the factor that come out of g here? So 1 over 4. Because here is 2 squared. So here will be 1 over 4. So, well, you can find what this is. 9.81 over 4. Go and calculate what it is. Okay, so that is how the graph will look like because of this relationship. The further you go, the weaker the field. But at this inverse square relationship. Now, I have one final question for you to think about, but I won't reveal the answer until the next one. The question is, this is at the Earth's surface already. What happens if you go inside the Earth? You dig a tunnel, go inside. What do you think the graph will look like before this point? Will it be a flat line? 9.81 all the way to the center of the Earth? Will it keep going up to infinity? So you go to the middle of the Earth, wow, gravitational field is infinity. Or will it go, I don't know, curve down to 0? Middle of the Earth, no field. Or will it do like that? So many choices. Think about it. We won't reveal it until one of the next videos. But think about what happens in here when you're inside the Earth. Below the Earth's surface, you dig into the floor. Okay? So that's the main ideas you need to know here. Okay? First things first, this equation, how to derive it. At the planet's surface, why is G constant? On Earth, how do you get 9.81? Where did this 9.81 come from? And of course, lastly, the graph of G proportional to 1 over R squared. All right, so that's all for this part of the theory. Now let's go and see some examples.